Hi, and sorry for the sound, but I felt like it is important that we summarize today's lesson before you move on to your homework. So, I would like to share with you this diagram. So, anytime when we have a line dilated over a point, we first will need to see if that center of dilation actually lies on the line itself or it doesn't. If it lies on the line, you could confirm it by taking its coordinates x and y and seeing if its equation is actually true. In that case, the image will have the same equation as the original line. It's much more interesting to see what will happen if the center of dilation does not lie on your original line. In that case, the image will have the same slope, but its y-intercept will change. And it will change depending on who your point is. If it's a random point, then you will have to find the y-intercept by construction. If you have a center of dilation as the origin, then you could tell for sure that the new y-intercept will be a product of your coefficient of dilation and the original y-intercept. So let's try to apply it using our first example. Let's analyze keywords. We have equation of a line. It's transformed by a dilation with a scale factor 2. So dilation 2. And the center is at the point 3, 5. So our first step is identifying that we actually are dilating a line in a point, and then identifying whether our point belongs to the line or doesn't. For that, we will copy our original equation, y equals 3x minus 4, and do the substitution for the x and y coordinates. Y would be 5, and we're checking if we can get it by multiplying 3 by our x coordinate, which is 3, and then subtracting the 4. 9 minus 4, we get a two-statement 5 equals 5, which indicates that 0.35 actually lies on the line. But that also means that this situation is just not what we're interested in. And since it lies on the line, we know the equation that you will receive as a result will be the same as the original. Therefore, the answer is choice 2. Next example. In this example again, line whose equation is given is transformed by dilation happens to be the same factor, 2, dilation 2. And this time it's centered at the origin. What is the image's equation? So the first thing to understand is whether or not the center of dilation, origin in our case, actually lies on the original line. For that, remember, we have to recall that origin coordinates 0, 0, we can use them to see if we make the equation true. So do we receive a 0 as a result of multiplying 3 by the value of x and then subtracting 4? No, because 0 is not equal to minus 4, it's actually a false statement, which means that our line, or rather the point of dilation, the origin, does not belong to graph we want to consider. This means that our image will have the same slope but change in the y-intercept. So to understand what kind of change in the y-intercept we will receive, we have to analyze once again the points of dilation. It's centered at the origin and not at a random point. Therefore, we will not be talking about that path. In fact, since it's dilated in the origin, we will be able to find the new y-intercept, who will be produced by multiplying your coefficient, that is 2, by the original y-intercept, who is minus 4. So it will be minus 4 times 2 minus 8. Given that the slope must be preserved and is 3, we will pick an equation that features the same characteristics. The first one then would be our pick. Next example. Very similar looking situation. We have a line. It is transformed by dilation with coefficient 2. This time, once again, dilation is happening over a random point, not an origin. Still, our first step is determining whether that point actually belongs to the original line or doesn't. So, the equation 3x minus 4 will be tested with the points 3 for x minus 2 for the y. Let's do the substitution. Will we receive minus 2 as a result of multiplying 3 by the x value and then subtracting 4? Well, 9 minus 4 produces 5. So left and right do not equal. This means that the center of dilation actually does not belong to the line. So we cannot pursue this path. The good news is that since the point of dilation does not lie on the line, we get a more interesting situation. We will have a similar line whose slope is the same, and we will have to find the change in the y-intercept. So let's ask ourselves once again, are we dilating in the origin or in a random point? Unfortunately, this time we are dilating in a random point. Therefore, our solution will be found only if we actually do the graphing. So let's quickly do the graphing. Original line, minus 4 is y-intercept. Minus 4. Here is a slope. We have 1 over. 1 over. Connecting the line. Now, center of dilation, 3 minus 2. 3 minus 2. Let's pick any point on the line itself, point that we can guarantee. Coordinates would be integers, which is at the y-intercept. We know that point is 0, minus 4. And it's convenient because when we dilate this point, we will see where it is located. And the image of that point will be our new y-intercept. I will do exactly what we did in class. You could see that I connected the point with the point of dilation, that's my line of sight, and I want to measure this distance, and I had a compass, I would then apply it. Since I have a positive coefficient of dilation, my image will be on the same side as the original. So from the point of dilation, I will see new image somewhere here on the same side of the original. So I'm going to check how I move from the point of dilation into the point with the y-intercept -4. Looks like I went down 2 and 3 to the left. So I will need to apply it twice. This was my first time, so I will go 2 more down and then 3 to the left. This will be my new point. Because this line will have the same slope, from this point I just found, I can apply that slope. 3/1 would mean that I found this next point that belongs to my image. And now having 2 of those points, I will be able to connect them and then extend them. Be very careful because your result depends literally on the quality of your plot. I'm noticing that the slope 3/1 could be continued, which is exactly what I'm going to do. Okay, I went exactly through those points, and as a result, I found the new coordinates at 0, 3, 0, 3. The choice for this question is choice 3. Next example. Transformation of a line by dilation 2, again centered in the origin. So we know that we need to check if the origin belongs to that line. So having x equals 0, let's see if the equation turns out to be a true equation. No, because 0 does not equal -4. That means that center of dilation does not lie on the line, which means that we're pursuing this line of thought. This indicates that we will have an image whose slope is preserved, but a new y-intercept. So let's once again check if we are dilating over the origin or over a random line. We are dilating over the origin. Therefore, this is not what we're interested in. And to find the y-intercept, we will need to work with the original y-intercept with -4 and simply multiply it by the coefficient of dilation, which will give us -8. And we know that the slope would be the same. So, having slope of 3 and the y-intercept -8 means that our